ducks under and goes for the Ashitori leg pick, but Yago is 80 kilograms heavier and he cannot pick up the leg. Yago has a frontal headlock on Enho and he's trying to smother him and take him out. But as we have seen from Enho before, he refuses to give in. Enho now has a belt grip with both hands. Yago doing everything he can to block Enho's offensive moves. Yago cannot get anything going because Enho's deep inside grip. Enho attacks and brings Yago down. What a magnificent effort by Enho to come out on top.
When I was a teenager, the equivalent of PlayStation 4 was a thing called the Commodore 64, and one of the interesting games was called World Games. It was basically an Olympic-style competition that had different sports chosen from different parts of the world, and they were sort of local, sort of niche sports. So you had like frisbee catching from California in the United States. You had a sport called caber toss from Scotland, where you have sort of a big wooden pole and you have to sort of lob it down a field and it has to roll in a certain way, and whoever gets it the furthest distance wins. And then for Japan it had sumo wrestling. I always used to like playing that one because it was some mix of throwing your weight around and actually getting in the right position to get leverage and win the match that way. And as I got older and started traveling to Japan, I started to watch it on TV when I was over there, and then the internet came along so I could watch it from back at home. And it's kind of a cool sport. You would think that there's a massive advantage to being tall and have a high weight, and there obviously is, but that's not everything. And so one of my favorite wrestlers, who you can see here, a little guy named Enho, who's the lightest in the sort of upper division, weighs in at about 99 kilos and often beats people almost twice his weight simply by getting just in the right position and then using rotational dynamics and their own weight to sort of carry them over, either outside of the ring or fall down onto the ground. So it's kind of nice as an example of rotational dynamics, and it's sort of nice as a sport where, you know, you can sort of get around weight advantage by being clever. If you ever get to see it live, highly recommend it, but you want to get in very, very fast for tickets, partly because they're very popular and partly also because the stadiums are quite small. And so if you're looking at seats near the back because you got in a little too slow like I did, don't let that put you off, because even at the back you get a really good view because the venues hold maybe 10,000 people or something like that. It's quite cozy and really good environment to see sports in. Okay, so in this lecture I want to carry inertia tensor forward a little bit and look at an interesting implication of linear algebra for this result. And we're not going to prove it because it would take us quite a bit of time and we'd have to get stuck into a quagmire of maths. And if you know your linear algebra properly, you can see why this thing comes about, okay? So what this thing relates to principal axes of inertia, okay? And so you'll remember we talked earlier about the fact that the angular momentum is in general not necessarily parallel to the angular velocity vector. It can point in some different direction, particularly for objects that lack symmetry. But you can choose axes for bodies where L is parallel to omega. And such an axis, when you choose it, is a thing called a principal axis, spelled P-A-L, principal as in the person who runs the school rather than principal P-L-E. And this thing actually comes about and is related to properties of the inertia matrix or inertia tensor that we built up in the first half of the lecture, okay? Now, an interesting thing that happens here is if your inertia tensor is diagonal, in the sense that you can write real numbers, real non-zero numbers down the diagonal and zeros off the diagonal, and some of you will be having flashbacks to your quantum mechanics course, and we'll get to that in a moment, then the x and y and z axes that you've chosen for that particular matrix will be what we call principal axes, and that means that if you choose to have a rotation about that specific axis, then L will inevitably be parallel to omega, okay? And the reason for that is that your products of inertia go away, and as we talked about yesterday, those products of inertia are the thing that drives L to be not parallel to omega, okay? If you're in this nice little situation in here, then you'll have three real numbers along this diagonal, and those will be things that we call the principal moments, okay? And they basically correspond to the moments of inertia in the coordinate system where the products of inertia are zero, okay? Now, one thing that pops out first is that if you have a symmetry axis through a particular origin in a rigid body, then that axis will be a principal axis, okay? And the two axes that are perpendicular to that will also be principal axes, okay? So for every principal axis, there'll be another two that are perpendicular to it. This is something that you exploit without knowing it in first year, because there you choose all of your problems so that there's a nice symmetry, and by choosing that nice symmetry, you know what the principal axis is. When you know what the principal axis is, all of the products of inertia go to zero, so you can sort of neglect them off to the side, and then all you've really got to do is deal with your moments of inertia, and you can keep that nice and simple and never talk about any of the complicated stuff, right? And that's why we've now got here to second year mechanics, where we've now had to bring in the extra pieces into this puzzle. The one really remarkable thing, and even to this day I still find it really surprising, and it's surprising because intuitively you kind of react against it and go, surely that can't be true. But when you do the maths, it actually, you know, you can prove it's true, and it definitely is true. You don't require symmetries to have principal axes, and in fact, for any rigid body you like, you can even take one where you've removed all the possible symmetry from the problem. You can take any point you like as an origin, and for that origin, there will always be three perpendicular axes passing through O that will be principal axes. And it's just a matter of working out what orientation they're in to do that, okay? And when you have those axes, then the inertia tensor will be diagonal, and you know that in that case, the angular momentum L will be parallel to the angular velocity omega, okay? And this comes about from a theorem in linear algebra that basically says that any real symmetric matrix is diagonalizable. And so if we pop back for 1 second here, you'll notice that this 3 by 3 matrix that we have for inertia tensor has a diagonal, fine, and then it has off-diagonal terms, and go back and have a look at the last lecture, you'll notice that the off-diagonal terms are symmetric all the way through. So there's always a symmetry about the diagonal in this matrix. And that means that it's always going to be diagonalizable. And so all you really have to do is just work out how to orient that system in order to do that. And you all realize exactly where that's taking us. That's taking us to eigenhell, place that you're all very familiar with from second year quantum mechanics. And so if our omega points along a principal axis, then what we should see our equation L equals I omega being instead is something that looks a little bit more like this. I omega equals lambda omega. And you'll notice in the last slide, I very strategically wrote that matrix as lambda 1, lambda 2, lambda 3 down the diagonal with zeros off to the side, because those are my eigenvalues, and I can then use those eigenvalues to extract my eigenvectors, and those eigenvectors are the principal axes, right? And in a lot of rotational dynamics questions, what you're interested in doing, particularly in engineering, is working out the principal axes so you can design your system so that L is parallel to omega, so that your rotational system is dynamically balanced in the sense that it spins smoothly about that axis without wobbles imposed by L not being parallel to omega and providing torques to the system, okay? I'm going to leave it quickly as an exercise in here to go back to the problem that we did in the first half of the lecture and get the eigenvalues and eigenvectors for that inertia tensor, and that will then get you the principal axes so you can understand which way this is going to rotate such that L is parallel to omega. I'll leave that as an exercise, okay? One thing you'll spot is that we're now having to deal with 3x3 matrices, and it means that getting our eigenvalues needs a little bit of a smarter approach. So let me go to that. When you have 3x3 matrices, it means that the characteristic equation for getting eigenvalues is going to be a cubic, and you need to be a little bit more clever about how you deal with those. And the strategy is somewhat similar to the lion here, hopefully slightly more successful. What you want to do is take the cubic, like a herd, and separate the weakest part off so you can solve it. So the trick usually is to try and factorize the trailing coefficient d, and then use the coefficients b and c to make an educated guess for what the little factor off the end is to get you a quadratic that remains, and then you just solve the quadratic by standard techniques so that you can get the 3 eigenvalues out, okay? I highly recommend actually taking some quadratics and some extra factors and building them up into cubics and just having a look at that process of coming back down again, because if you've never done it, it's not easy. But once you've done, you know, half a dozen cases, you kind of get a feeling for what this thing looks like, and usually you can kind of tease it out. A lot of things that come up in exam problems, in particular cubics, are not impossible to solve. You just got to use that approach, and it should pop out fairly quickly. Okay, one of these things where experience really pays off later on. The next thing I want to come to here is the kinetic energy for a rotating body, and what I want to get is a very useful expression that we're going to use later on. And so we're going to start with our usual expression for kinetic energy. T is a half sum m alpha v alpha squared, and we're now going to basically just work this thing out in terms of vector cross products, but we're going to do this with a couple of mathematical relations that pop along the way. So the first step here is to write this as a half sum m alpha, and we'll remember that v is omega cross r, so this is now going to be omega cross r alpha, just here, squared. Okay, so we're going to use two really common tricks for handling vector cross products. And I've mentioned this in earlier lectures. I used to have a book where I keep these noted down. Some of the reason why I want to do this maths is to get a result for later on. One of the nice side effects of it is I get to show you two really useful relations that turn up again and again and again in higher year physics. So the first one is for two vectors A and B, we know two things. We know A dot B is just A B cos theta, where theta is the angle in between, and A and B are just the magnitudes. And A cross B is going to be A B sine theta, okay? So we can write a little relation here that looks like this. A dot B plus squared plus A cross B squared is now just going to be A squared B squared cos squared theta plus A squared B squared sine squared theta. And you can see where I'm going with this. The cos squared theta and the sine squared theta are going to become 1. So this is just A squared B squared. And so what we can do in here is basically write that A cross B squared is equal to A squared B squared minus A dot B squared. Okay, really useful relation. Use it quite a lot to reduce cross products into something a little bit more manageable in terms of just a scalar product and a vector product, dot product. And so what that means, if we apply that just up above, our T is now a half sum over m alpha omega squared r alpha squared, and they're just magnitudes, omega dot r alpha squared. And let's call this equation 1 because we're going to use it later on. Okay, I'm going to come at it from a different route now. So we need another relation here, and this relation, I grew up in a rough neighborhood. I've always remembered as the ACab rule. So let me write it down first, and then I'll show you why I call it this thing. So what we have here is A cross B cross C. And what I know to do here is that because the B and the C are inside the brackets, they're the things that pop out, right? So I've got a B over here and I've got a C over here. And then the thing that comes in the middle here is two dot products. So what I have is A dot C and A dot B. And then when you live in a rough neighborhood, any association with cops is a negative. So there's a minus sign in the middle of here. And so you can see why how I remember this thing. I basically just build it up from the name of the rule, the ACab rule. Okay. There's all sorts of other names for it, but they don't really help you remember it quite as well as that. And it's another case of you should personalize them to yourself because that's the way they're the most meaningful. But if you can build yourself little mnemonics to member things on your way through your problems, then that's actually usually really helpful. Okay, so what we have here is we're going to start in a new point L. And this is a really common thing in physics problems. You come down some line of algebra, and then you stop and you pick up somewhere else and you try and join the two ends up, okay? So this thing is going to be some M alpha, R alpha cross V alpha. And of course, as we saw in the in the first half, this can be written as R alpha cross omega cross R. And so now you can see why I want to use ACab rule here. This thing is going to be some M alpha omega. Actually, I've got to put an R in here. And so this is where I've got to be really careful decomposing this thing. This is A, this is, let me just go to color for a second. This is A, this is B, and this is A, okay? And so basically I just got to drop them into the right places in here. So I've got B first, then I've got A, so that's R alpha cross, sorry, not cross, dot. The whole point of it was to get rid of the cross product. Dot C, which is R alpha. Minus C, which is R alpha, A, which is R alpha, dot B, which is omega. Okay, so I just got to decompose this thing carefully and properly. What I want to do is take omega dot L, okay, and this is now going to be omega dot some M alpha omega R alpha dot R alpha minus R alpha dot omega, like so. Make that a square bracket on the end just to be clean. And what I can do in here is bring my omega through. And at the moment, really, if you think about this, all I'm doing is just playing around. And sometimes if you go on to do theoretical physics, sometimes this is actually your job, is just to play around with mathematical things and see if you can work out where things might hook up. And a lot of this is not necessarily just random playing around, it's inspired. You kind of know where you're going and you just have to sort of feel your way there. So what we're going to do here is we're going to bring this dot product with the omega out the front to the inside. And so this is now going to look like sum over M omega of there's two components, so we're going to put the dot product into both. And so what we're going to have is omega dot omega R alpha dot R alpha minus omega dot R alpha dot omega, like so, okay? And so, of course, keep our M alpha. Omega dot omega is just omega squared. R alpha dot R alpha is just R alpha squared. And then on the end, we've got two dot products, but dot products commute, so it doesn't matter which order we have them. So this thing on the end here is omega dot R alpha squared. And if we just slide back up for a second, you'll notice that we've got our expression for t back. Okay, so this thing is actually equal to 2t using 1. And so final step in here is basically just to say that t is equal to a half omega dot L. Okay, and kind of a nice, really nice way to pop out kinetic energy in terms of two things that you would know in this problem, L and omega, and you can get L quite easily once you know the inertia tensor. Okay, there's one other aspect to this to notice, which is that this equation implicitly tells us that L is not always going to be parallel to omega, right? Because there's going to be a dot product in here, and the angle between them will affect the amount of kinetic energy that we have in our system. Okay, so there's a flow on from this, which is that if we use a set of principal axes as our coordinate system, if we're basically doing this problem in terms of principal axes, then our dot product here, omega dot L, becomes basically the diagonal times a vector, so you end up with, you know, omega 1 L1, lambda 1 omega 1, lambda 2 omega 2, lambda 3 omega 3, and then your kinetic energy pops out as something rather simple. It's just a half lambda 1 omega 1 squared plus lambda 2 omega 2 squared plus lambda 3 omega 3 squared. Okay, so it's just a nice simple expression when you diagonalize that system up in there. Okay. The interesting last observation in here, and I'll let you prove this one for yourself, in linear motion, there's a very similar relation as well, and it looks like this. It's a half v dot p. Okay, I'll let you check for yourself that that thing really holds, but what we just got is basically the rotational equivalent of that expression. And one thing you're probably getting familiar with now is that pretty much for every linear motion equation, there's a corresponding rotational motion equation. Okay, so I want to finish off this lecture with one last example, and it's basically to loop back onto the beginning of the lecture itself, where we looked at an example in a gyroscope of precession. Okay, so what we're going to do here is deal with a symmetric top spinning at a point O with an angle theta to the vertical on an axis that's one of the principal axes. Okay, and so the first thing that you'll spot here is that I've already used my XYZ coordinate system for my sort of space about this origin where we're spinning, and I kind of need to set up a new set of axes to deal with my rotational motion. Okay, and so what we often do is call these E1, E2, E3. They're all unit vectors, and usually we set E3, which is sort of our z-axis, to be the dominant rotation. Okay, so to simplify just about any problem, you look for what the dominant rotation you're interested in. In this particular case, you've got something spinning that then is going to spin in another axis because of the precession. And you choose that dominant rotation to be E3 and work from there. It usually makes the problems kind of easy. Okay, so we know that we're dealing with principal axes, so we're only going to have diagonal elements in our inertia matrix here. And the other thing is that we know that it's symmetric about that axis, and so what that means is that lambda 1 is going to be equal to lambda 2, and so we can make those two things the same. Okay, and so the problem in here is basically what we want to do is find the angular velocity of precession about the z-axis. So basically what's going to happen here is that this top's going to be spinning, it's trying to fall over. That gravitational force is going to combine to give a torque that makes the spinning top basically work its way around a cone about that z-axis. Okay, and we want to work out what the frequency of that is. Okay, and again we're going to reuse a variable. So here we're going to use our big omega here as a way of keeping track separate to the little omega, which is the angular velocity around that principal axis E3. Okay, so the way I'm going to start this problem is I'm going to switch gravity off and set the problem up, and then I'm going to turn gravity on and work from there. Okay, so we have a top spinning on its own axis, and at the moment all we really care about is just the rotation of this disk and this axis here, right? So we automatically know what the angular velocity vector is. It's just omega E3 hat. And I'm using the hat there because it's a unit vector. And then I can get the angular momentum in this case as well. Okay, so angular momentum just here is going to be lambda 3 omega, or lambda 3. Actually, it's a little typo just there. Let me clean this up. What I'm going to do here is have essentially I omega. And what I'm going to pop out here is lambda 3 omega E3 hat. Okay, just to be really clean with my notation. Okay, so at the moment there's no torque on this system because there's no forces acting. Okay, but because there's no torque, then L is constant and the top will just happily spin right where it is, right? So if you went up onto the space station, took a top, made it spin and set it at an angle like this, it wouldn't fall under gravity, it'd sit right where you put it, and it would just stay there happily spinning round and round in circles. And then if you imagine switching gravity on, now there's going to be a force acting to try and tip this thing, and it's going to generate a torque. Okay, so let's switch gravity back on, and what we're now going to have here is a torque. And the torque is going to be, as you know, the R that it's acting about cross the force, right? So this is going to be R cross F, as you know it. And again, the R is at the front, like almost all rotational equations. And so here, this is going to be our vector R, which is, you know, where the force is acting about, because the center of mass will act about that origin, cross mg, and we can turn g into a vector in this particular case as well. Okay, and so the magnitude here would be r mg sine theta in this particular case. Okay, and it's going to have a direction that's perpendicular to both r and mg, and so if we take the plane that's been set up by mg and r, it's going to be perpendicular to it, and it's actually going to act that way. So what it's going to do is try and drive this top around, because as it acts here, now it's going to rotate that plane, it's going to act there, it's going to rotate that plane, act there, rotate that plane, act there, and keep going. So it's basically going to drive this thing around. Okay, all right. What we're going to do here is assume that the torque is weak, okay? And so what that means is that any of R and M and G are small compared to all the other parameters, just to keep the problem from becoming really unmanageable. And so what it means when we turn this torque on is that dL on dt is no longer going to be 0. And if dL on dt is no longer equal to 0, then our omega 2 and omega 3 are going to stop being 0, right? Our rotation about this E3 axis is not going to stay there on its own. We're basically going to try and get rotations about other directions because that angular momentum is trying to change. And the important thing that we use here actually is that the torque is equal to dL on dt, or L dot, okay? And this is basically the rotational equivalent of Newton's second law. So Newton's second law, you're familiar with, force equals dp on dt. Here we've got torque equals dL on dt, right? So what we can do in here is take this equivalence, and of course we have an expression up here for our L. So what we're going to get in here is R cross mg is equal to the time derivative of this term up here. And of course, lambda 3 is fixed. And it's fixed because it's a property of the body, and the body's not going to change, right? Assuming it's rigid. Omega is not going to change, not immediately if we don't have, you know, something that's actually damping the rotation, right? So in a real gyroscope, you'd have friction that would reduce omega, but if this thing was freely floating, then omega is going to stay the same. So the only thing that can change here is E3, right? So this is going to be lambda 3 omega E3 dot. And I'm now going to put the dot instead of the hat, and I know that this thing is a unit vector anyway, right? So what this equation basically is telling us is that the orientation of E3 is going to change. In other words, this top is going to change its orientation. We now can work out that R here is basically just R E3 hat, right? And we can see that in this particular problem. It's basically going to be the spindle of the top here, and so it's always going to point along E3. And then, of course, G is just minus GZ, okay? I can use Z hat here. You could use K hat if you want to. It's perfectly interchangeable. There's no requirement for either. And then what we've got to do is basically just isolate out E3 dot. Okay, so if we come back to our equation 1 here, E3 dot is going to be R E3 hat cross minus MGZ hat. Let's just put that there for a second. And then we're going to carry our other two terms, lambda 3 and omega, over the other side. So we've got something that looks a little bit like this here for a moment, right? And you know, for the cross product, we can basically pull all of the coefficients out the front. The other thing we can do is we know that when we swap the terms in a cross product, we have a minus sign, right? It anti-commutes. So this thing is going to be MGR on lambda 3 omega Z hat cross E3 hat. Okay, like so. And of course, this thing we could write basically as omega cross E3 hat if we want to, and then basically define our omega vector here as MGR on lambda 3 omega Z hat. Okay, and so what we've got is basically a change in E3 with a particular magnitude, and we're going to get a precession from that torque acting around this thing, okay? And so now we know the frequency of it. It basically just depends on the mass, G, which is a constant, R, which is basically where the center of mass is relative to this origin point O, because that's the center of mass is going to be where the gravitational force acts. Lambda 3, which is a property of the body, and omega, which is the speed that we set up. And we could calculate this and measure this thing. And in a normal term where the teaching labs are fully open, you would do exactly this experiment. You would set up a little gyroscope, you would measure the precession rate and relate that to the geometric properties that we just calculated and verify for yourselves that this thing is true, okay? And so what you get is a motion that looks a little bit like this. So here's your spinning disc on above a pivot point. You'll notice at first it bounces around a little bit trying to stabilize itself. We'll talk a little bit about what that effect is in the next lecture. And then you'll notice it settles into this nice steady precession around that pivot point at the bottom, torque acting to drive it around. And if you calculate that angular frequency of precession, you will find that it fits that equation that we just got, okay? Really nice place to finish, so I think we'll stop there and I'll see you next time.
And Goedo is actually out in the crowd. Look at that. Never see Hakuo throwing salt like that. So yeah, Goedo in his retirement look, not in his sumo look. Is also one of the commentators. All right, here we go. Let's turn it up just a little bit. Hakuo knows what he's going to do. It's like, I don't want you getting in on me, getting no hold of my leg or nothing. Oh, he's got a belt. He's got a belt. He's got a leg. No! That's awesome.